As per the principle of homogeneity, it says that all the terms of the physical equation must contain the same dimension. Since both L and G have the powers 1 by 2, we can write T is equal to K into root of L by G is the final expression. In the given equation, all the terms do not have the same dimension. We can say that the given physical equation is dimensionally incorrect. Hello everyone. Welcome to session 6 of chapter 2, Units and Measurements. In the last session, we had discussed about how to write the dimensional formula, what are the uses of dimensional analysis, in which we have studied about how to verify the correctness of the given physical equation. So, the given physical equation will be having certain terms on both the sides like LHS and RHS. If all the terms have the same dimensional formula, then we can say that the given equation is dimensionally correct. Let us see now what if the equation do not contains the same dimensional formula on both the sides. So, we have an example, v square is equal to u plus 2ax. Here in this equation, let us write the dimensional formula for LHS. I have v here. So, v is nothing but velocity. Velocity dimensional formula is m raised to 0, l raised to 1 and t raised to minus 1. Since I have v square, so I should write the dimension to the power 2. Next, I'll get m raised to 0, l raised to 1 into 2. So, I'll get l raised to 2, t raised to minus 1 into 2. So, we will get t raised to minus 2. So, this is the dimensional formula for v square. Similarly, let us now move on to RHS. So, I have a term called u in the RHS, which is nothing but the initial velocity again. So, since it is velocity, I am writing the same dimensional formula m raised to 0, l raised to 1 and t raised to minus 1. Now, as per the principle of homogeneity, it says that all the terms of the physical equation must contain the same dimension. But here we have v square is equal to m raised to 0, l raised to 2 and t raised to minus 2. U is equal to m raised to 0, l raised to 1 and t raised to minus 1. So, the dimensions of these two terms are not matching. So, let us now see the another term, that is 2ax. Here 2 is a numerical digit which do not have any dimensions. So, I am not considering 2 in our further steps. So, next I have a and x, where a is acceleration and x is the displacement. So, acceleration dimensional formula is m raised to 0, l raised to 1 and t raised to minus 2. And again we have a displacement and the dimensional formula for that is L. So, let us now simplify this. So, simplifying these two, we will get m raised to 0, l raised to 1 I have here, 1 I have here, 1 plus 1 is 2 and t raised to minus 2. Now, observe this and this carefully. So, are they same? No, because we have l raised to 1 here, l raised to 2 here, and here also we have l raised to 2, but here we have l raised to 1. Since in the given equation, all the terms do not have the same dimension, we can say that the given physical equation is dimensionally incorrect. So, let us now see one more application of dimensional analysis, that is to derive the relationship between various physical quantities. To explain this, I have considered an example of time period of a simple pendulum. So, we know the general expression for time period of simple pendulum, that is t is equal to k into root of L by G. But how to derive it, how to arrive at the expression with the help of dimensions, let us see it now. The period of oscillation, which is denoted by a letter capital T of a simple pendulum, depends on various parameters such as length and the mass of the bob and acceleration due to gravity. Derive the expression for its time period using the method of dimensions. As the question says, the time period depends on the length and the mass of the bob and acceleration due to gravity. Since we do not know what is the exact dimension, we are considering it the powers as A, B and C. Later, we will derive the values for these variables. So, as of now, we are taking time period is dependent on the length of the pendulum, the mass of the bob and acceleration due to gravity, and hence the quantities L, M and G are raised to powers A, B, C respectively. So, to remove this proportionality, we have to introduce a constant to equate these two quantities on either sides. So I am writing T is equal to, I have introduced a constant called K, which is nothing but the proportionality constant, and hence it do not have any dimensions. So L raised to A, M raised to B and G raised to C. So I'll call this entire equation as equation 1. Here K is a proportionality constant which do not have any dimensions. So let us now write the dimension of all the terms. So what do we get? So we have to write the dimensional formula for all the terms. So T is nothing but M raised to 0, L raised to 0 and T raised to 1. Since it do not possess any mass and length, it has only time. So the dimensional formula is M raised to 0, L raised to 0 and T raised to 1. And K is nothing but the proportionality constant. It has no dimension. So we are just neglecting it and writing the dimensions for all the other terms. So we have length here. So L, which is enclosed in a square bracket, which is raised to A, and M is nothing but mass, again capital M, which is enclosed in a square bracket, which is raised to a power B. G is nothing but acceleration due to gravity. So acceleration dimensional formula is L T raised to minus 2. And it is also enclosed within a square bracket, which is raised to a power C. Now we get M raised to 0, L raised to 0, T power 1 in the LHS, and here we are just rearranging the terms as per this order. We are getting M raised to B, L raised to A, and one more L we have, which is raised to the power C. Since the bases are same, powers gets added up. So L raised to A plus C and T raised to minus T. So now you can observe we have MLT in LHS, MLT in RHS. The bases are same and hence we can equate the powers. So now let us equate the powers. So equating the powers of L, M and T on both the sides, we get A plus C is equal to 0. So how is that? See here, L raised to A plus C and L raised to 0 we have here. So A plus C, which is equal to 0. So we are writing A plus C is equal to 0. Next, in the place of B, M raised to B, we also have M raised to 0. The bases are same again. Powers can be equated and the value of B is equal to 0. Now let us look at this. T raised to minus 2C, T raised to 1, which is nothing but minus 2C is equal to 1. So we need the value of C. So let's take this 2 to the denominator. We'll get the value of C is minus 1 by 2. So now after calculating the value of C, we can calculate the value of A. Because we have A plus C is equal to 0. The value of C is minus 1 by 2. So A minus 1 by 2 is equal to 0 and A is equal to plus 1 by 2. So the value of A is plus 1 by 2, value of B is 0 and the value of C is minus 1 by 2. Now we got all the values of the powers. Let us substitute this in the first equation to arrive at the final expression. And the first equation is T is directly proportional to L raised to A, M raised to B and G raised to C, or T is equal to K into L raised to 1 by 2, M raised to 0, G raised to minus 1 by 2. So how did we get this? Because here proportionality is replaced by a constant T equals K, L raised to A, M raised to B and G raised to C. So here K as it is I am retaining. In the place of A, the value obtained for A is substituted. In the place of B, the value obtained for B is substituted. And in the place of C, it is minus 1 by C and the value is substituted. And the expression from this we can write T is equal to K, L raised to 1 by 2, here M raised to 0. So it is not necessary to consider that. And we have G raised to minus 1 by 2. And that can be written as divided by G into plus 1 by 2. Here in the numerator it is minus 1 by 2. When it goes to denominator, we will get G raised to plus 1 by 2. Since both L and G have the powers 1 by 2, we can write T is equal to K into root of L by G is the final expression. So this is how the method of dimensions helps us in deriving the relation between various physical quantities. Let us see one more example for the same. Here we are going to derive the expression for centripetal force. So to derive the expression for centripetal force, we are considered a particle which is moving uniformly in a circle. So if a particle is moving uniformly in a circle, it depends upon its mass, its velocity and the radius of the circle. So as the question says, the force, the centripetal force of a particle which is moving in a circular manner depends upon mass, velocity and radius. We can write the expression F is directly proportional to M V, R, which are raised to the powers A, B and C respectively. Since the dimensions are not yet calculated, we can raise the powers as the variables, that is A, B and C respectively. Or we can write this equation as F is equal to K into M raised to A, V raised to B and R raised to C. Why K here? Because it is proportionality in the above expression. To remove the proportionality, to equate the equation, we have to introduce a constant, and K is nothing but a dimensionless constant. So now let us write the dimension of all the terms. So what do we get? Let us see. For force, the dimensional formula is mLt raised to minus 2. So how to get this? We know F is equal to m into A. So m is nothing but mass, A is acceleration. The formula for acceleration is Lt raised to minus 2. So the force dimensional formula is m into L into T raised to minus 2. And we have here m raised to A, V raised to B and R raised to C. So let us write the dimensional formula. M for mass. So it is enclosed in a square bracket which is raised to a power A. Next we have velocity. Velocity's dimensional formula is Lt raised to minus 1, which is enclosed inside a square bracket and it is raised to a power B. And also we have radius. Radius dimensional formula is L, which is raised to a power C. So now let us simplify this and we'll write the equation. We are retaining the same thing which is there in the LHS, that is mLt raised to minus 2, which is equal to m raised to A. L, we have 1 here power and to the whole power B. So 1 B is a B. One more L we have which is raised to a power C. Since the bases are same, the powers gets add up. So we'll get L raised to B plus C and T raised to minus B, because we have T raised to minus 1 into B, which is nothing but minus B. Now we can observe mLt on both the sides. Since the bases are same, we can equate the powers. So equating the powers on both the sides for L, M and T, we get A is equal to 1. So how? We can check here. M raised to A we do not have anything here in the LHS. So it is nothing but m raised to 1. So it is A is equal to 1. Next, check this. L to the power B plus C in the RHS and L to the power 1 in the LHS. So we can write B plus C is equal to 1. And next we have T raised to minus B, which is equal to T raised to minus 2. Since the bases are same, the powers gets equated, which means minus B is equal to minus 2. So since we have minus on both the sides, they get cancelled and the value of B we get is 2. So now let us calculate the value of C. How to calculate the value of C? We have B plus C is equal to 1 when B is equal to 2 plus C is equal to 1 and C is equal to 1 minus 2 and the value we get is minus 1. The value of C is minus 1. So substituting the value of A, B and C in the first equation, we get F is equal to K into M raised to 1, V raised to 2 and R raised to minus 1. Because the equation was F is equal to K, M raised to A, V raised to B and R raised to C. Now we are substituting the values what we get for A, B and C in this equation and hence we got F is equal to K into M raised to 1, V raised to 2 and R raised to minus 1. Since we have R raised to minus 1, we can bring this to the denominator and we can write it as R raised to 1. So the equation becomes F is equal to K into mv square divided by R is the expression for the centripetal force. So this is how we can derive the relationship between various physical quantities with the help of dimensions. Let us see what are the limitations of dimensional analysis. So the first one is dimensionless quantities and the proportionality constants cannot be determined by this method. For proportionality constants, we cannot write the dimensional formula for few proportionality constants. So if the constant of proportionality also possesses dimensions, this system cannot be used. Next, this method is not applicable to trigonometric functions, logarithmic and exponential functions. So the trigonometric functions like sin theta, cos theta, tan theta and also for logarithmic and exponential functions, we cannot apply this method of dimensions. So in the case of physical quantities which depend upon more than 3 physical quantities, this method will be difficult. If the quantities are less than 3 or which is equal to 3, then we can easily go with the method of dimensions. But if it is exceeding the 3 physical quantities, then this method is difficult. A dimensionally correct equation need not be actually an exact equation, which means the dimensional analysis tells us whether the equation is dimensionally correct or not. It cannot say that the given equation is absolutely correct or not. So that is one of the major drawback of the dimensional analysis. So this completes the chapter units and measurements. In today's session, we learned what are the advantages and disadvantages of dimensional analysis. But in the chapter called units and measurements, we came across so many interesting concepts, and also we came to know that how these measurements are applicable, how these knowledge of measuring concept helps in our daily life. So in the next session, I'll come up with another interesting chapter. Until then, take care all of you. Thank you.